All right, our plan today. I'm going to do section 6.5, 20 minutes maybe. The remaining hour or so, we're going to do some optimization review questions. That's the day, right? What happens next class? That optimization mini test. We'll do the 6.4 is the other section for chapter 6. And we'll figure out what we're going to do next week as soon as I see like a tentative schedule of times or whatever. Probably we'll wait and do the test 6 after Irish week and we'll just fill in the blanks next week with the weird schedules. I think it's probably for everybody's best, right?
Yeah, absolutely.
All right. So what we're going to talk about today is the average value of a function. So how do you compute an average?
Slow add them all together and you divide it by the number of terms.
Exchange, you divide by exchange.
Great. So how are you going to do that for a function where there's infinitely many points?
Let's see. Same way.
So that's what we're going to talk about today,
Over.
right? So, you know, like, okay, we take this, you know, this is some y coordinates from a function, and divide by the number of points that we've chosen, right? And since we're talking about all the points from like A to B along some function, right? So you have like right, you have some function, you're adding up all the points along there. So this you know, the number of points that we're going to be taking from here is going to be b minus a divided by the gap between our x's, right? So if this is like, you know, 1, 2, 3, 4, 5 spots, it's going to be this distance between the x's. That's what we're talking about as the delta x, right? So we can kind of rearrange this. We can substitute the b minus a over delta x in, and then we like multiply by the reciprocal, and we get like this thing, and whoa, I recognize something like this, right? That's a sum, and that sum is just like the basis for our integral, right? That's a Riemann sum that we're talking about there. Oh yeah, okay. So at the end, what tumbles out is our average value for a function formula, which is just 1 over b minus a, the integral from a to b of f of x dx. That's it. So what are we really talking about, right? This is an area under the curve, right? This is like the width of a curve, right? So if I take an area divided by the width, that's kind of like getting, if the area is a rectangle, if the shape's a rectangle, you're getting a height out of it. Now, even if it's not like you know, like this is our area. This is from like A to B. What we're talking about is finding like a height where that area of the rectangle would be the same as the area under the curve. That's that special height that we're finding there. This is like our average value for the function. It's just the height that's going to give you a rectangle that's going to have the same area as the area under the curve. Is everybody okay with that? Now, is that height guaranteed to be a value on the function? No. Unless that function is continuous. If you have a continuous function, that height will be a value on the function. Otherwise, it may or may not exist, right? All right, so let's do an example. So here it just asks to find the average value of the function f of x on the interval from -1 to 2. So that's my formula. So we're just gonna plug in so far so good. What's the antiderivative of 1? X. What's the antiderivative of x squared?
X cubed divided by 3.
X cubed over 3. Going from -1 to 2. So 2 plus 8/3 minus -1 minus -1 cubed over, well, I just write. So that's a plus, right? 8/3 plus 1/3 is 3, and 2 plus 1 is 3, so that's 6 over 3, so that's just 2. So if we look at the picture to imagine what we just did, let's do that. Oh, that's not what I want. I want this. Okay, so we have 1 plus x squared, and we're going from -1 to 2, right? Okay. And this probably should go back up to normal. Right. So I'm looking at this area under the curve, right? And we found the average value was 2. So the area of this rectangle is going to be the same as the area under the blue curve. That's what we just found. So the height of that rectangle should be 2. That's what the average value is telling us. Does that feel okay? Now, in this case, there's 2 places, there's 2 values of x. It appears that our function takes on that average value. That doesn't have to happen though, right? Does that feel okay? Doesn't have to happen unless we are continuous. So if the function is continuous, then there has to be at least one place where the function is going to cross that average value. All right. That theorem is called the mean value theorem. That's the MVT. Again, we'll abbreviate that with 3 letters. You can use that abbreviation on with me or with the AP. They will all recognize that as standard abbreviation for the mean value theorem. It says that if f is continuous on the closed interval from a to b, there exists a c on that interval such that the average value is equal to that. Or you could think of the integral from a to b, f of x dx, the area under the curve is equal to the area of the rectangle whose height is the average value. Right? You could use it either way. So again, visualizing what you're doing. Area under the curve is the blue. Your average value is this height C. The area of this rectangle should be the same as the area under the curve. You can kind of see that we could take that piece and move it down there, should fill that space. And there is one value on the curve f of x that takes on that height f of c, right? Does everybody feel okay with the picture, kind of what we're talking about, visualizing it? This tends to be a fairly easy concept because it's so visual, right? You can see, okay, that makes a ton of sense. We're just finding a rectangle that has the same area as this gobbly-gop shape. Okay, perfect. So let's do 2 more examples, and we're Audi 5000 on this one. Sound good? Okay. So example 2 says, since f of x equals 1 plus x squared is continuous on the interval -1 to 2, the mean value theorem says that there is some number c on that interval, -1 to 2, such that this is true, right? Everybody's okay? From our example before, we know that f of c was equal to 2, right? We found that earlier. So if I want to find what is c, so I subtract 1 from both sides and square root, I get the c is, maybe I'll write it this way. And that is a c. C is plus or minus 1. So those are the places on that function where the graph takes on that average value, which if we go back and we look at our picture, matches up, -1, +1.
That's where they match.
Exactly. Yep, where the average value is the same as the value of the function.
So that's how you can check?
Yep. Does that feel good? Everybody's happy? Fairly easy idea, right? Nothing complicated going on. I think also nicely intuitive. Let's look at one more example, and we'll call this quits for today. Says, show that the average velocity of a car over some time interval, t1 to t2, is the same as the average of its velocities during the trip. So let's say we have some position function s of t. So our average velocity should just be our change in position divided by change in time, right? Everybody's okay with that? The average of the velocities would be like the average, right? Yes.
What does it mean by, like, what is the question asking? Like, what does as the average of its velocities mean? How's that different from the average velocity of a car?
Well, the average velocity is just starting position, ending position, difference in the two positions, the displacement divided by time. Here, at instant 1, we're going 25 miles an hour. Instant 2, we're going 30 miles an hour. Instant 3, we're going, so we're adding up all the velocities we went along the way. Should come out to be the same thing, because velocity changes.
Good morning, Notre Dame Prep. Please excuse
excuse this interruption. At this time, faculty, staff, and students, we are going to conduct a tornado drill. This is just a drill, this is just practice.
So we're trying to show that the average velocity is the same as the average of the velocities. So we've set this up. So we need to do our integral here. Oops. What is the integral of velocity?
Position.
Position, exactly. Yes, that's right.
Wow.
Which is just our S of t. So then we plug things in, and we'd have S of t2 minus S of t1, which is the same as the average velocity.
Oh, wow.
Does everybody feel okay? I like to do that one because it's, again, refresh ourselves on some of these velocity, position, acceleration relationships. A little bit of physics for you. Is everybody cool? That's it for 6.5. That's the entire idea, just average velocity or average value of a function. There's a formula. Formula is easy to remember. Yes, sir.
If you go back to the first example, like on the last one, when I'm confused why it's not like plus, like isn't it minus 1 plus minus 1 over 3 or no?
So it's 2 plus 8/3 plus 1 plus 1/3.
No, I thought it was like 2 plus 8/3 minus
Right,
1 plus 1/3.
but we're plugging a -1 in, right?
Yeah.
So it's minus -1 minus -1 cubed, which is -1 over 3. So
Isn't
the
it plus -1 cube? Or no? Like I
So-
thought it would be.
so yeah, so you could, there's a parenthesis around that, so the negative would distribute through,
Okay.
so that they're both subtracted. Is that
Yeah.
okay? You feel good? Okay. Everybody 6.5 okay? More or less?
Yeah.
Yeah, the homework should be relatively straightforward. There's just a few problems, not even much to do. What I want to do today then is some optimization review. So I built a review to do on the MyP. We can, I think it's probably best for us to do this kind of together and give you guys a chance to work, and we'll go through it, If you want to follow along, this is on the MyP. If you like, I can't see the details from the back of the room, feel free to pull out your tablet, look at it on the MyP. So I made the review assignment here for today, and I signed it, so if you look at the assignment center or whatever in there, you should be able to see it. Relatively easy.
Does it have examples from like all 3 kinds of, is there 3 or 4?
I think it's a fair representation of what I would expect you to be able to do. So there's multiple choice and free response. It's just this opt practice.
Let's do it.
So, you know what I'm gonna do? I think it's gonna be better for display purposes. If you wanted to look at your MyP, that's fine, totally fine. You wanna follow along in there, that's totally fine. You wanna put answers in there, that's totally fine. I am going to drop the questions into the OneNote, just because it'll be, this is not what I want. Where did I put this? Damn it. One moment while I get this straightened out.